high tech. Just so the other picture shows building the fuselage, the empennage, and wings. Here we are integrating the avionics and mission equipment into the airplane, putting in the electrical harness and so on. This done in another facility. Okay, so I mean, as you can see, it's a great picture, but it shows how using engineering principles and software to evaluate where the stress points are. You always want to take weight out of anything that you have to get up in the air. So where can we take it weight out? Where do we have to have it to carry the loads? And just a picture of someone doing some electrical testing on the bench. Let me get out of that slide. So, this picture in the upper left, it has to do with radio frequency, RF energy. And, you know, there are several things to consider that require technical discipline. And so these are the people that I don't quite understand. I'm sort of a mechanical engineer by design. And the electrical engineers actually believe in RF energy and all that. So they insist that it works. So, so anyway, with an airplane like this, there are a couple of things. One, you may be giving off RF energy that could be interfering with something else. And we've had to work through some problems where an infrared nose camera was giving off radio frequency emissions that were interfering with the data link. And it took us a long time to sort that out. So the upper left-hand picture is an anechoic chamber where you can put it in and it basically prevents emissions from, you know, there's RF energy all over where we're surrounded by here. And so that isolates it from it, and then you can bombard it with, you can either take readings see what's coming off the equipment in the airplane, or you can bombard it with RF energy to see if it's susceptible, see if somebody sends the right sort of frequency, could they make the controls go haywire and crash it. I think you all know about the airplane that the girl that went down in Iran a while ago, I think was trying to see everything. I'm not quite sure what happened, but it could be that it had an RF susceptibility. So that's our airplane being tested in an anechoic chamber. The other picture is just you can see it looks like a halfway. We just needed a place to test engines. We're trying to put a more powerful engine on, so you start with bench testing. So, okay, how do you test an engine? Well, you get your engineers and figure it out. So we just came up with this design where we could we open the back door of the garage there and fire up the motor, and we can evaluate its performance just using. We designed it ourselves. It works great. Likewise, the next one down is to test the strength of the wing. The right here flies commercial, right? So you just assume that somebody somewhere took the time to make sure the wing is playing strong. Well, since about the Wright brothers on, the way you test the strength of the wing is you turn the airplane upside down, you load up the wing with sandbags. Because when it's flying, the wings, the pressure is in the upward direction, so you tip it upside down, you stress it till it breaks. And then you see what broke, and then you fix that, then it gets stronger, and then you do it again. So we designed our own test fixture, and I'm pleased to say the first thing we did was we broke the rig. So we knew we had a strong wing, but then we had to design a stronger test fixture. So the other was just a picture of a test. Just from the field, not too far away. Yes, sir.
So that launcher picture that you just showed, you're just saying the lower left. Can you tell us what kind of pressure came to launch this? How about magnitude?
I'm trying to think. I think something like, I'll say a number that will be way off. So I don't know.
Because we were launching 2-liter bottle rockets.
Okay.
And And at 100 PSI, we were lucky at 50 feet. So I was wondering, would we compare it to your?
Let me break for lunch. I'll better text you.
Yeah, hopefully you watch better than me.
Oh, okay. Okay. So we are, again, just expanding on the anechoic chamber testing. One is at Penn State, the other one, OSU, UML, it stands for Oklahoma State University University Multispectral Laboratory, and they have an RF chamber down there. So I guess I'm assuming that you're all interested in why would somebody want to go into engineering, why would they want to go into technical discipline? I love the Navy, and I love this because I don't do this every day. So we just kind of in a roundabout way found out about this in Oklahoma. Oklahoma State is serious about getting into the unmanned air vehicle business, and they stood up an engineering curriculum dedicated to unmanned air systems. And so we started talking with them. The next thing you know, they bought one of our airplanes, and we go down there and fly and support it. And then we started looking at research and development programs. And in fact, this call that Bill is on, the University Multispectral Laboratory is a program manager for that. So I guess the variety of what we get to work on in engineering is appealing. We talked about overseas deployment, so with our Navmar employees sweating the heat. Those pictures are from Iraq, so they're a little bit old. But, this one's there. Logistics, engineers and logisticians, I've seen, they do this. But really, logistics, which is, most people think of just packaging something, handling it, transportation, storage, I think of logistics, but there's a lot more to it, interfacing in the design of an airplane, thinking about the logistics. If you're going to have build a product that's going to be 8 time zones the other way and a lot of border customers to get through, you want to think about how am I going to support this thing. And if I'm always having to send landing gear that are very heavy, then I'll probably better design a better landing gear, that sort of thing. So I guess that's, logistics is mentioned there. Let's see. Okay, another thing our company does, this is the case where that's a forward operating base in Afghanistan. And about, 2.5 years ago, the forward operating base, we send our kids there, right? So we owe protection. And so one of the forward operating bases got attacked, and they took on some pretty serious mortar fire. So we realized that we really weren't doing our job protecting them. So this became a very top priority of the Pentagon to get the ability to see 360 degrees around and out at least 10 kilometers to be able to detect anyone approaching. If you can protect that perimeter, then you pretty much prevent being attacked, and you can see people planting IEDs and so on. So this was a crash program, and there are other people built the. We just went out and found people that build the aerostat, still with helium, but then we helped with the systems integration. So okay, just so you put this big balloon up in the air, but unless you have cameras and radar and acoustic sensors, and signal intelligence sensors up there, and then that information has to get sent down to a ground station. It has to be fused into such that an operator can make sense of it. And all that is, it's the sort of thing that you could spend years doing. You have to get done quickly, so we're real proud of that. So here's just a picture of what it looks like over base, and it's a real success story. We're really proud of that because they found that the the attacks on the bases just almost went to zero. Even if the sensors were working, as soon as the tethered aerostat went up, the enemy knew that they were probably being watched. So, real interesting project. Scott killed us. We worked weekends and okay. Tech Shark Block 3. I don't know. So I guess this is in Yuma, Arizona, where we do our R&D testing. You can see it's got some winglets on it. And again, the design engineers did the computational fluid dynamics, and you can increase the lift over drag ratio so you can get better endurance and better fuel specs if you put winglets on. We recommended it, the customer tested it, they didn't think they saw the improvement. They weigh 4 pounds, so they said we'd rather take 4 extra pounds of payload. So that's not good. Well, if we build one, we're putting them on. Wiggling them. So they just go ahead and throw it up the flight line, coming in for a landing. So, nose camera used for navigating, taking off, and also some of it. But underneath this turret that's got the sensors in it. The operator on the ground can control it, pointing where he wants. And data is recorded. It's streamed live to the ground control station and then recorded there as well as viewed live. Technician doing final checks. We're just not all of them have this. This is a new antenna that is for a high-speed, high-bandwidth data link. And it was just a late addition. This, research and development developed at Johns Hopkins University, developed this data link. They came to us. They said we need an antenna. It's got to be about this size. Where should we put it? Engineers figured out that's where it is. Works great. We love pictures of airplanes. So. Just some of the different sensors. And that's it. So that's that's the unmanned air vehicle program. Now, one of the early slides, Jim said that we do a lot of different things too. So we do